Hey there guys, Paul here from theengineeringmindset.com. In this video we're going to be taking a look at air-cooled chillers to find out how they work in a more advanced way. So we're going to be taking a look at the refrigerant this time and the pressures, the temperature, the enthalpy, entropy, the flow rate and the heat transfer, as well as the air, that cooling air that's taking that heat away from the system, and the flow rates of that, the temperature and the heat transfer, and also the chilled water, the flow rates, temperature and heat transfer for that. And as always, we'll be looking at the metric and imperial units for this. Now, in the previous video to this on air-cooled chillers, we took a very basic look of how they work, and we're just going to go around the system looking at each of the components in there. So if you haven't checked that video out already, I would highly recommend you went back and did so. There will also be a link at the top here where you can just click on and it'll go straight to that video. We've also got a video just like this on water-cooled chillers and how they work, and we go through each of the system components and have an understanding of that as well. There should be a link up here as well for that one. And we've also got an advanced version of the water-cooled chiller, so check out that video if you're into that level. And then again, we look at all the pressures, enthalpies, entropies, etc. around the system for a water-cooled chiller. But anyway, let's jump in and have a deep look at how air-cooled chillers work. Now, the first component we've got there is the compressor. Then we've got the condenser up the top there. Then we've got the expansion valve over here. And lastly, we've got the evaporator down the bottom there. We've also got the fans at the top here, which we will be blowing or sucking air across the coils of the condenser. And we've got a filter dryer here as well, but we won't worry about that in this video. Now we're going to look at what the properties of the refrigerant are at 4 key points throughout the air-cooled chiller. So we've got point 1 there, just between the evaporator and the compressor, so the refrigerant, the properties of the refrigerant before it enters into the compressor. Then we have point 2 there, and that is just after the compressor and before the refrigerant enters into the condenser. Then we have point 3 there, which is just after the condenser and just before the expansion valve, and we have point 4 there, which is just after the expansion valve and before the evaporator. And we're going to plot these on a graph just to see how these change throughout the system. So on our vertical axis, we're going to have temperature on one graph and pressure on the other graph, and on the temperature graph we're going to have the entropy along the horizontal axis, and on the pressure graph we're going to have the enthalpy going along the horizontal axis. And we're also going to have our saturation lines on the graphs as well. So if we mark point 1 on the graphs, and you can see that point 1 is obviously there. Now before we go around and see what the properties of the refrigerant in the air and chilled water are on this system, please remember that these values may not represent what you have on your chiller in your building. They will almost certainly be completely different from this, and you should check with your manufacturer for what your values should be. This is just a theoretical educational video for them. So at point 1, we know that the refrigerant there should be a low pressure, low temperature, saturated vapor. And the refrigerant at this point would be around 350 kPa or 3.5 bar at 5 degrees Celsius, 41 degrees Fahrenheit, with an enthalpy of 250 kilojoules per kilogram or 107 BTUs per pound, and an entropy of 0.916 kilojoules per kilogram per Kelvin or 0.219 BTUs per pound per Fahrenheit. Now point 2 we know is going to be a high pressure, high temperature superheated vapor. So we'll just mark point 2 up in the superheated region. And there we find that the state of the refrigerant at state 2 is the pressure is 1500 kPa or 15 bar, a temperature of 6 degrees Celsius, 140 degrees Fahrenheit, with an enthalpy of 280 kilojoules per kilogram, which is 120 BTUs per pound, and an entropy of 0.916 kilojoules per kilogram per Kelvin and 0.219 BTUs per pound per Fahrenheit. Notice in this one that the pressure has increased as well as the temperature. The enthalpy is also increased, but the entropy has remained the same, and that's because we're compressing the refrigerant here. So we'll just plot that line for that from point 1 to 2 on the graphs. At point 3 we know the refrigerant should be a high pressure, medium temperature saturated liquid, and that it's going to almost certainly be on or very close to the saturation line on the graphs. So here we can find that the pressure has remained the same at 1500 kPa or 15 bar. The temperature has decreased, so it's lost obviously some thermal energy there through the condenser, and that's now 55 degrees Celsius and 131 degrees Fahrenheit. The enthalpy has also decreased to 129 kilojoules per kilogram, which is 56 BTUs per pound, and the entropy has also decreased down to 0.458 kilojoules per kilogram per Kelvin, or 0.109 BTUs per pound per Fahrenheit. So we can now plot that on the charts as well, just that line from point 2 to 3. Now point 4 we know is going to be somewhere within the vapor dome, so we can put our values just within there. And here we'll find that the refrigerant, the pressure has reduced down to 350 kPa or 3.5 bar. The temperature has also reduced down to 5 degrees Celsius or 41 degrees Fahrenheit. That's because it's expanded. The enthalpy has remained the same at 129 kilojoules per kilogram or 56 BTUs per pound. And the entropy has slightly increased at 0.483 kilojoules per kilogram per Kelvin, which is about 0.115 BTUs per pound per Fahrenheit. So we can plot that on the graphs as well, going down from point 3 down to point 4. And then we can also plot the final line, which goes from point 4 back to point 1. Now the air that's blowing across the condenser to cool that refrigerant down and remove that unwanted heat from the building, we're going to say in this scenario that this chiller is going to have a volume flow rate of 30.75 cubic meters per second, which is about 30,750 liters per second. The temperature going in is around 30 degrees Celsius at 86 degrees Fahrenheit, and the temperature out would be around 44 degrees Celsius, 111 degrees Fahrenheit, and that would result in a heat transfer of 496 kilowatts. And you can check that from the difference in enthalpy between points 2 and points 3. So that difference in enthalpy from here to here, multiplied by the mass flow rate of the refrigerant. So the mass flow rate in this system is 3.3 kilograms per second, or 7.2 pounds per second. It's using a refrigerant of R134A, and the compressor power, the compression power, is 98.9 kilowatts. We can find the compressor power by finding the difference between enthalpy 2 minus enthalpy 1, and then multiplying that by the mass flow rate of the refrigerant. And then we can also see the properties of the chilled water there. So from this we can find that it's got a flow rate of 15.8 kilograms per second, which is about 34.8 pounds per second. The temperature in, so that's the temperature coming in from the building after it's collected all the unwanted heat within the building. So that's going to be flowing in at around 12 degrees Celsius, which is about 53.6 degrees Fahrenheit. And the temperature coming out of there, once it's given up all that unwanted heat into the evaporator, and that refrigerant has taken it away off into the compressor, round into the condenser, where it rejects that heat and comes round. So by the time the chilled water leaves the evaporator to go off around the building again and collect that heat, that should be around 6 degrees Celsius, which is about 42.8 degrees Fahrenheit. And that means the heat transfer for that would be 397 kilowatts. And you can check that as well by finding out, subtracting the difference in enthalpy between point 1 and point 4 and multiplying that by the refrigerant flow rate, and that will give you the heat transfer. Now if you like this video, then you'll probably want to check out this video as well, which we made, which is the cooling coil calculations. And you can see there we go through the full calculations. So you can tell for a cooling coil in an AHU or a fan coil unit, the air in, the air out, and the cooling load. You'll calculate what the temperature of the air coming off the coil is, and you can use that in the air cool chiller calculations as well, exactly the same formula. And in the video we also show how to calculate the condensate mass water flow rate, so all the condensated air you're pulling out, moisture you're pulling out of the warm air that's coming into the building. How much water can you extract from that? But anyway, thanks very much for watching. I hope this has helped and that you've enjoyed watching this. If you have any questions, please leave them in the comments section below. Don't forget to like, subscribe and share this video. Once again, thanks for watching.